Welcome to the Bible and Science. This is Dave Prentice. I'm a retired public high school teacher, certified in all branches of science and math. I've also taught on the Bible and Science for many years, both in the U.S. and on many overseas mission trips. This is episode 16 of the Bible and Science. Something we've been touching on, we're going to focus a lot on today, which is how persuasive is the case for a Big Bang. A lot of people have the idea that a Big Bang is proven scientific fact. Now, as you're going to see, it's not. If you're trying to deal with the origin of the universe, this can be broken down into many areas. The four major areas that I break it down into are: number one, how did matter and energy come into existence? And we've already dealt with that and seen that there is no known natural explanation for that. So we have to appeal to unknown processes. They could be natural processes or non-natural processes. Creation is definitely not a natural process. Okay, so once matter and energy came into existence, how did they get from there to their present state? And later we'll touch on the question of how did life begin, and once life began, how did it get from there to its present state? So how did matter and energy get from whatever condition they were in at the beginning to their present state? We were talking, kind of tap dancing around the Big Bang, which requires the universe to be an enormous size. And we were dealing with how big is the solar system. And so let's touch on how we say we know how big the whole universe is. You could picture it as a ladder, and there are rungs on the ladder of cosmic distances. First, you determine the Earth's average distance from the sun by triangulation. We talked about using Kepler's laws and then bouncing radar off planets and so forth. So we use math to determine the average distance of the Earth from the sun. And then there are some stars that are called main sequence, quite a few of them, and we use those and determine what's their distance if they're less than about 50 light years away by parallax. And then we assume from that point on, a lot of assumptions, that nothing is distorting our view. So then we use the spectral class of the star to calculate its absolute brightness. Then we assume our calculations about the absolute brightness are correct. And we apply those values that we obtain to calibrate the distance of thousands of other stars in the main sequence. Then we find Cepheid variable stars that seem to be near some of the main sequence stars from step 3. It's complicated, I know. We assume that the relationship between period and brightness is the same for all Cepheids throughout the universe. I'm not going to quiz you on this, though. Then for number 6, we use those Cepheid variable stars, some of which are in other galaxies, to determine how far away do we think those galaxies are by some pretty complicated mathematics. Then we assume that the brightest stars in each galaxy have the same absolute brightness. We then use those to calculate further distances. And then for the most distant galaxies that we're able to see, we use the redshift of the whole galaxy in something called the Hubble relation to determine what we think the distance is. So I mentioned main sequence stars. There are lots and lots and lots of main sequence stars. So we put them on something called the Hertzsprung-Russell diagram, named after the astronomers Hertzsprung and Russell. And they've determined the Hertzsprung-Russell diagram depends upon the spectral class BAFGKM, which used to be told among the astronomers as BA fine girl kiss me. Well, that sounds pretty sexist nowadays, right? But we match the spectral class with the absolute magnitude of the star. What's absolute magnitude? If I look at a 200-watt light bulb from 2 feet away, it's going to hurt my eyes. But if I look at it from 2 miles away, I'm barely going to see it. What's its absolute magnitude. It's the number of lumens put out by that light bulb. So I have to make a lot of assumptions if I'm trying to determine the distance by using the absolute magnitude. I have to know what the absolute magnitude is. We see bright dots through our telescopes. So I say, okay, this is its absolute magnitude at a specific distance, a certain number of parsecs. And then now that we've got its absolute brightness, we can calculate its distance. But in order to calculate its absolute brightness, we had to know how far away it was. So the Hertzsprung-Russell diagram, the main sequence, leads us to conclusions that are based on circular reasoning. We depend upon the distance to know the magnitude, but we need the magnitude to know the distance. That's circular reasoning. Everything farther out than this depends upon this distance calculation, which is based on circular reasoning. And then some Cepheid variable stars are found on the main sequence on the Hertzsprung-Russell diagram. Cepheid are named after ancient mythology, but these are stars that get brighter, dimmer, brighter, dimmer, brighter, dimmer, brighter, dimmer periodically. So we pick some that are on the main sequence, and we decide we can tell what's their distance based on absolute magnitude and magnitude based on distance. So we use some of the Cepheids that are found on the main sequence as standard candles for more distant objects. So here's another major assumption. The astronomers assume that the relationship between their period of going bright, dark, between the period and the absolute brightness is the same for all Cepheid variable stars throughout the universe. How can you confirm that? You can't. There's no way to know if that's really true or not. In fact, there's not even a way known yet to know why they vary from bright, dark, bright, dark, bright, dark. We're working with assumptions here. So the universe is big. How big? Well, anyway, there are too many variables to be sure about its exact size. But to make the math work, to make the calculations work, the evolutionary astronomers invent the concept that the brightest stars in each galaxy must be the same absolute brightness. Well, how do you know that? There's no way to be sure that's true. If the Bible's correct, it's not true, because the Bible says, for one star differeth from another star in glory. So the evolutionary astronomers don't stop there. They assume that the brightest supernovas in each galaxy all have the same absolute brightness. Why should they? There's no reason except to make the math work. So that causes a serious problem. At least 20 supernova, probably more, around the universe are dimmer than the theory predicted. So the most obvious explanation would be that, oh, maybe the theory's wrong. No, can't accept that, because that might say, well, maybe the universe isn't as big or old as we think. So how do we know what's happening out in space? The light that's coming to us on Earth has characteristics of both waves and particles, the wave-particle duality. So by analyzing the wave-like characteristics, we can determine things about what the source was doing when the light was emitted and how the light has behaved since it was emitted. So there's a little, no quiz again, there's a little diagram showing the relationship between frequency and wavelength. If A to B represents 1 second, then the upper wave has a frequency of 4 hertz, that is 4 cycles per second. The lower would have a frequency of 8 hertz. But if instead that represents distance of 1 centimeter, then the upper one would have a wavelength of 1/4 of a centimeter. The lower would have a wavelength of 1/8 of a centimeter. So for very short wavelengths, we use billionths of a meter, nanometers. A nanometer is 1/billionth of a meter. So visible light that you can perceive with your eyes ranges from a wavelength of about 390 nanometers, which is extreme blue, to about 760 nanometers, which is extreme red. So for all electromagnetic radiation, such as light, frequency times wavelength equals the speed of light. So you ready for a test on that? No, I'm not going to test you on that. But this has to do with how we determine how far away these distant objects are. The Doppler effect has to do with relative motion between the source of a wave and the recipient of the wave. So it applies to both mechanical waves such as sound or electromagnetic waves such as light. If the mechanical wave or electromagnetic wave is moving toward an observer or the observer is moving toward it, the wave seems to be of a shorter length, shorter wavelength than the actual value. So if the two are moving apart, the wavelength seems stretched out. So the Doppler effect you've probably heard on the weather reports. Weather radar determines how the clouds are moving. If something's moving away, the actual wavelength is going to seem to be longer. If it's moving toward you, the actual wavelength will seem to be shorter. So we also use this to determine our motion through the cosmic microwave background radiation, which we'll get to shortly. We also use it to determine how the distant stars are moving relative to us. So at the bottom, you'll see if that was the actual wavelength of a star's light, that would be the spectrum we expect to come to us from hydrogen. Then if it's moving away from us, then the wavelength would seem to be stretched out toward longer waves. That's greatly exaggerated, of course. But if the object is moving at us, then the wavelength would seem to be compressed, and this also is greatly exaggerated. So what are we talking about when we say a redshift? This is how we say we know that the universe is moving and stuff like this. Okay, so reports of the universe expanding are based on the colors of light, the wavelength of light from stars that are shifted toward the red end of the spectrum, which is interpreted by evolutionary astronomers that it's a Doppler shift and the star is moving away from us. So in the middle and the bottom of the page, you'll see the actual wavelength versus stretched versus compressed, red shift, blue shift, and normal. So is there any other possible explanation for redshifts besides the universe expanding as a leftover from the Big Bang? Well, we don't understand how things are really moving out in deep space, but it's possible if two objects are moving sideways relative to each other, rather than just a straightforward outward expansion, if they're moving sideways, we could see some redshifts from that. It would take hundreds of years of observation to be sure that none of the redshifts of starlight are transverse effects. And then gravity distorts light, it bends light. So light passing through the gravitational field of a massive star, such as the one it came from, would start its journey with a gravitational redshift. Dust out in space to a certain extent can absorb light and re-radiate it toward the red end of the spectrum. And we're about to get to relativistic redshifts. And then there could be a bunch of stuff we don't know. Okay, guess what? We don't know everything. So we use something called the Hubble relation that says the velocity of a distant object is directly proportional to its redshift. How do we know that? The Big Bang really messes around with Euclidean geometry. It says that space is curved. Well, is there any such thing as a straight line at cosmic distances? It's questionable. And we depend upon something called Hubble's constant, which unfortunately is not very constant. It's anywhere from 50 to 100 kilometers per second per megaparsec, depending which direction you're measuring and what equipment you're using. So that's an uncertainty of 100%. That could be due somewhat, at least, to gravitational redshifts. And there have been some astronomers that contend that the redshifts are actually proportional not to the velocity, but to the square of the velocity. If so, that would mean the stars are much closer and moving much more slowly than we previously thought. So here's how we talk about the curvature of space. If I shot a laser beam forward from my eyes and I waited long enough, since space is supposed to be curved, eventually that laser beam would come around and hit me in the back of the head. What? So according to classical physics, which depends upon Euclidean geometry, if the universe was expanding, space was already there. And the universe expanded through three-dimensional space, so points A and point B move apart through space. That's classical physics. That's what we're familiar with. But then if you're going to depend upon relativity and the Big Bang, you need to appeal to non-Euclidean geometry. The universe doesn't expand through three-dimensional space because there is no such thing as space outside of the matter and energy cloud. What? There is no space except where matter is present. So matter defines space. So past the edge of the expanding universe, there's no such thing as space. So space is expanding because it's part of the Big Bang, but points A and point B, they're keeping their same relative positions in space. Yeah, you didn't know you're going to get into physics, did you? So think about an ant. Okay, I'm going to try to illustrate to you something called four-dimensional space. There was a wonderful book called Flatland, and I recommend if you're interested in this to get into that book. So imagine that there's a two-dimensional ant who's trapped inside the surface of a piece of paper. He has no concept of up or down because there is no up or down to him. He's trapped inside the surface. So even if the paper is curved into a sphere, a very big sphere, he has no way to know it. He can only see his immediate area. Okay, hello, ants. You're ants. I'm an ant. According to relativity, we are the ants, but we don't know it because we're trapped inside the three-dimensional surface of a four-dimensional hypersphere. Space is curved, but we have no way to detect it. So if there's a two-dimensional ant confined to the surface of a sphere, like I have on the picture there, he's on the surface. He doesn't understand there's anything outside or inside. He's just on the surface. He could never reach the center or the edge because from his perspective, the surface has no center or edge. To the ant, it's unbounded. So if space is a four-dimensional hypersphere, as many Big Bang models say, we're confined to its three-dimensional surface. We can never find the center or the edge because neither one exists. Four-dimensional space would have to be unbounded. So no matter where the ant goes, things look pretty much the same in any direction. There's no preferred frame of reference. Likewise, all of the Big Bang models assume that no matter where we go in space, things on a large enough scale will look pretty much the same in any direction. The reason I say all of the Big Bang models, there's not just a Big Bang theory or a Big Bang model. There's a bunch of them, and they all contradict each other in key ways. So the idea that things are going to look pretty much the same in any direction is philosophy. It's not science. If there is a preferred frame of reference, as a Christian, I believe God's frame of reference is preferred, then at least some parts of relativity and a lot of parts of the Big Bang are wrong. So speaking of the Big Bang, is it valid science or is it just a big bust? There are three possible explanations for the universe. Number one, it's all just properties of matter and energy, materialistic evolution, atheistic evolution. Or it could be that there's some sort of a God who started it and is letting things run along by theistic evolution. He's influencing evolution. Or it could be that there's some sort of divine creation involved. How often have you been told any of the arguments for theistic evolution or divine creation? Probably seldom, if ever, you're continually being bombarded with the idea of atheistic evolution, an atheistic Big Bang. Well, I'm hoping to show you some problems. Remember, evolution says we have natural processes only. And as Dr. Todd said in Nature magazine in 1999, even if all the data point to an intelligent designer, such a hypothesis is excluded from science because it's not naturalistic. And this goes back to what Watson wrote 70 years earlier. The theory of evolution itself was a theory universally accepted not because it could be proved by logically coherent evidence to be true, but because the only alternative, special creation, is clearly incredible. So I want you to think about some of the contradictions between Genesis and evolution. Genesis tells us that God did it. The universe, earth, and life were produced by the direction of action of God. Evolution says, no, it was purely natural processes. Genesis says God created time and he created matter and energy from nothing. We have no idea how. And evolution says random chance processes created space, time, and matter from absolutely nothing. We have no idea what the process were. Genesis says creation was a completed event. Evolution is supposed to be an ongoing process. Genesis says everything was created in distinct, clearly defined steps. Evolution has supposedly occurred by continuous processes. Genesis tells us that the earth was formed in darkness first, and then God said, let there be light. So the earth came first and then light. Now, that's not what the Big Bang says. The universe began in a flash of light called the Big Bang. The earth appeared billions of years later. So there was light first and then the earth. Genesis says the sun and stars became visible on the fourth day after the earth. So from the earth, you could see the sun and stars on the fourth day. The earth came first and then the sun and stars. Evolution says, no, the sun and stars were there billions of years before the earth ever came along. So the sun and stars came first and then the earth. Genesis tells us, in the beginning God created the heavens and the earth. The earth was without form and void, and darkness was upon the face of the deep. So from the very beginning, the earth had a liquid water surface, whatever the deep was. It had water when you read Genesis chapter 1. But evolution says the earth began as molten rock. And so for billions of years, it was too hot for water to exist as a liquid. So there was land first before liquid water, compared to the Bible, which says liquid water first and then dry land. Genesis says at least until after Adam sinned, it had never rained on the earth. Evolution says from the very beginning it was raining. Genesis tells us the sun was created a day after plants and insects a day later. So this would really strongly imply that the days were not millions or billions of years, but they had to be literal 24-hour days. Most plants can't reproduce without insects, and in order for them not to become extinct, the insects had to be there, so the days could not have been millions of years long. But those that want to believe in an atheistic universe have to say, no, in order for evolution to fit into Genesis, each day would have had to last for millions or billions of years. Now, I have a certain amount of human intelligence, but I'm not as smart as God. And God, I believe, inspired the Bible, and he gave Moses the things to say, to write down. So he said what we're familiar with in Genesis chapter 1. But suppose God had used evolution and he wanted to express it in biblical language. Is that too complex? No, not at all. He could have said, when God began to create the heavens and the earth, darkness was upon the face of the heavens. And God said, let there be light. And there was a great blast. Those are all King James words. And after many days, God made the stars, the sun, and the earth. And the earth was without form and void. And God caused the land to appear, and he fashioned the deep. And God made the exceeding small creatures and plants that teem in the sea. And God blessed them, saying, be fruitful and multiply, and bring forth the fish, and the great sea monsters, and the creeping things, and the birds of the air, and the beasts of the field. That would fit with most ideas about evolution. That's not what the Bible says. It's a clear contradiction. If God used evolution, it would have been easy for him to say so. So let's think about where the universe came from. Suppose you're you walk into a room and there's a fried egg on a plate. Okay, you could come up with various ways about how that fried egg got there. You could believe there was a cook. Or if you absolutely refuse to believe in the existence of a cook, you could say, well, I don't know, maybe a supernova released a burst of energy that traveled through space, bounced off a satellite, and hit a chicken. The chicken exploded, and one of its eggs was so hot that it got fried and the shell cracked and fell away. And it was sailing through the air and there was a window open, a window closed, but suddenly a field appeared, a force field opened the window, the egg came sailing through, and then the force field came back and it closed the window. So is that plausible to you? Well, was there a cook for the universe, or was there a whole bunch of unexplained, unexplainable natural processes? I can't explain the process God used. Nobody else can explain the process that a Big Bang would have used. So why do people believe in the Big Bang? I really should put these in reverse order. That's what they've always been told. Nobody ever gave them any sort of an argument to the contrary. And then also the redshift of starlight and the existence of the cosmic microwave background radiation, or CMB. Those are the reasons that people use to support the idea of a Big Bang. Mainly, that's what they've always been told. Not many people have investigated it for themselves. So I want to ask you big questions about the Big Bang. Supposedly, matter and energy came into existence in the form of a singularity, an almost infinitely dense ball of matter and energy, probably less than the size of an atom. Okay, well, we already dealt with the question of how it came into existence in the first place. We have no answer for that. Okay, so the next question, this thing is so massive, what could make it explode in the first place? There is no answer. Evolutionists don't have an answer for that. They just say, well, it did. And then they say, well, in order to produce the present universe, it would have been expanding far faster than the speed of light. And then it would have had to slow down so things had time to form. Okay, so the next question, in order for inflation models like that to be correct, the expansion had to speed up far faster than the speed of light and then slow down an incredible amount. What we've seen within our experience, and this has to do with Newton's laws, no exception ever observed, is that in order for motion to change, there must be some sort of a force. Well, what forces would have appeared suddenly to make this thing not only explode, but then expand far faster than the speed of light and then slow back down to the present rates? What forces would have made that happen? The answer is, oh no, we have no idea. So if there was this big explosion called the Big Bang, it would have left perhaps remnants, and there is a cosmic microwave background radiation field out in space. Its energy level is about 2.73 degrees above absolute zero. We can measure that with the right equipment. So at the time of the Big Bang, when this little singularity exploded, present theory says that the temperature, the energy level, would have been billions of degrees. Matter would have been changing to energy, and energy would have been changing back to matter, back and forth, back and forth, back and forth. But then as the primordial fireball expanded, the matter and energy would have begun to cool like the gases in a refrigerator when they expand. So after about 300,000 years, matter and energy in the Big Bang would have decoupled. So the energy went right through the matter without affecting it. The energy level of radiation would have been still about 3,000 kelvins at the time. That's the problem. That's more than 1,000 times too hot because it's now down under 3 Kelvin. So in order to explain the change from 3,000 degrees to 2.73 degrees or kelvins, the evolutionists have to say that the energy was absorbed by the fabric of space as space expanded. That means space had to be four-dimensional. Space itself had to be expanding, not things expanding through space, but space was expanding. It's not possible in a three-dimensional universe. I don't want this to turn into a cosmology class and scare everybody away. We're almost finished with talking about the Big Bang. So we'll continue on next time, and then after that, we're going to start talking about the origin of life. And you can't explain that by natural processes either.